Suppose if you have a allyl phenyl ether 32, then you can follow the path A and path B for the disconnection approach. And resultant will be, suppose the path A leads to the formation of bromobenzene and allylic alcohol. And if you are following the path B, what will happen? So during the disconnection path B, you will get the phenol and the allylic bromide. So during the disconnection, of course, you will get the two types of four types of reagents, but you need to be cautious which path needs to be followed in order to reconstruct it. We might prefer route B because phenol is much more acidic. You know that the phenol is much more acidic. The pKa corresponds to the phenol is pKa is 10 than alcohol, such as this is 31. So when you compare the 33 and 31, the pKa value of phenol is 10 over the pKa corresponds to the 31 is 15. So in this case, the phenol is requires an less acidic, or weaker base is sufficient in order to deprotonate it and generate an oxyanion. The weaker base such as NaOH can be used for this kind of part B reaction. NaOH can be used, but the main reason to prefer route B is that route A will not work. So even though not only with respect to the pKa, the pKa, even though if it is 15, if you are available with any other strong base, could able to generate this oxyanion, but the problem is you cannot perform this reaction. Oxyanion won't attack over the carbon which is carrying the leaving group. The nucleophilic aromatic substitution, particularly with this particular site, is difficult. That's why you cannot use these two reagents in order to construct the target molecule of 32. But as and when you have this phenol as the starting material and allylic bromide as another reactant, then it is easy. Because first thing is pKa favors, the pKa is 10, weak base is sufficient to form an oxyanion, and formed oxyanion can attack over the carbon which is carrying the leaving group, resultant will be formation of the allyl phenyl ether of 32. The nucleophilic substitution on bromobenzene do not work, while those on allylic halides, these allylic halides such as 34, work very well indeed. So I think these kind of reactions you can check it out in the chapter 2 or 3 in the case of retrosynthesis analysis by Stuart Warren. Okay, so here the coming to the synthesis part, take the part B synthetic equivalents, these two. The first take the phenol, then use the base NaOH. You will get the alkoxy, that is a phenoxide ion, then followed by the 34. 34 you need to introduce here in the second step. Then oxyanion will attack over the carbon which is carrying the leaving group. Resultant will be formation of allyl phenyl ether. So this is the allyl phenyl ether. The note is that a disconnection we did not consider for a moment would come from reversal of the polarity in ether CO bond. So in either CO bond, in either side CO bond. So CO bond we have not considered the reversal of polarity. So reversal of polarity means considering oxygen negative and then carbon negative and oxygen positive. So because in the previous case we have thought that only oxygen should carry a negative charge in this case as well as this case. What will happen suppose if you make this positive and then the other side as a positive, or like this. So take the same target molecule. Instead of disconnecting at the CO of this, try to do the CO disconnection. Then you may propose one of the synthetic equivalent of this carbon is negatively charged and Li plus. Of course, this reagent is available. You need to think about the next reagent in order to reconstruct this target molecule. Trying to improve the disconnection we might suggest a nucleophilic phenyl species. This is a nucleophilic phenyl species such as 36. Perfectly all right. So this reagent is available commercially and you can use it too. And electrophilic oxygen reagent. So this is an electrophilic oxygen reagent. such as the hypochlorite 37. This is hypochlorite. So wherein oxygen carries a positive charge. Hypochlorite, definitely not at all right. So if you're using these kind of reagent in order to react with this 36 in order to get the 32, of course you need to. This is not a good idea. If 37 existed, it would be dangerously explosive. So that's why this reagent is explosive. So during the synthesis, you need to be conscious. It should not be explosive material. You need to take all the precautions in order to reconstruct the target molecule.